Hello dear student, myself Prof. Sukhbir HK. Today we learn new topic thermodynamic state variable. In this topic we firstly discuss what is meant by thermodynamic state variable. A state variable is any measurable or observable characteristic or property of a system when the system remain in a equilibrium. A state variable is any measurable or observable characteristic or property of a system when the system remain in equilibrium. For example, see here pressure, volume, temperature, density and mass of the system. Mass of the system. It is also a term as property of a system. Thermodynamic state variable also called as a property of a system. See notes here. These are measurable properties and are called macroscopic variable of a system. These property are measurable property and are also called microscopic variable of a system. Then we see here intensive or extensive variable. What do you mean by intensive and extensive variable? Firstly, we discuss intensive variable. Intensive variable. Intensive variable do not depend on size of a system. Intensive variable do not depend on size of a system. Consider a system in equilibrium. Let this system be divided into two equal components, each with half the original volume. The pressure capital P, temperature capital T and density rho are the same as in the same as initial in the both compartments. This variable is called as a intensive variables. Second one, extensive variable. What do you mean by extensive variable? Extensive variable depend upon the size of the system. Extensive variable depend upon the size of a system. Consider a system in equilibrium. Let this system be divided into two equal compartments, each with half the original volume. Let's consider the total mass. The total mass capital M and the internal energy U of the system, however, gets equally divided into two compartments. Thus each compartments, now this mass we consider here m by 2 and internal energy U by 2. Hence this system or this variable are extensive variable of the system. In this way we consider here what is meant by extensive system and what is meant by intensive system. Question asked on this topic, what is state variable of a system, and another one, explain the term intensive and extensive variables. Next one we consider here what do you mean by thermodynamic equilibrium. When can you system is said to be in thermodynamic equilibrium? What do you mean by thermodynamic equilibrium? See this definition. A system is said to be thermodynamic equilibrium when the following these conditions of a equilibrium are satisfied: simultaneously mechanical equilibrium, chemical equilibrium, and thermal equilibrium. This system or this equilibrium is called as a thermodynamic equilibrium. Okay, firstly we discuss here what is by mechanical equilibrium. Mechanical equilibrium. For a system to be mechanical equilibrium, there should not be any unbalanced force acting within the system and between the system and its surrounding. Also, this pressure in the system should be same throughout the system and should not change with time. Next one, thermal equilibrium. For system to be in thermal equilibrium, the temperature of the system should be uniform throughout, and it should not change with time. A system when the thermal equilibrium is described in term of state variable. In state variables, and third one, chemical equilibrium. Chemical equilibrium. For a system to be in a chemical equilibrium, there should no chemical reaction going within the system. There is no transfer of matter from one part of the system to be other due to diffusion. A system to be in chemical equilibrium, its chemical composition has to be same throughout and should not change with the time. This is a three condition of a three condition for a system in a thermal equilibrium. First we discuss mechanical equilibrium, then we discuss thermal equilibrium, and third one we discuss chemical equilibrium. These three condition of equilibrium can be satisfied, then this equilibrium is called as a thermal equilibrium. Whenever some unbalanced forces exist within the system, they will get neutralized with time attain the condition of a equilibrium. This is a very important note. Whenever some unbalanced forces exist within the system, they will get neutralized with time to attain the condition of a equilibrium. Next one, we consider another term, equation of a state. What is meant by equation of a state? The mathematical relation. What is meant by equation of state? The mathematical equation between the state variable is called the equation of a state. For example, for an ideal gas equation, the state is the ideal gas equation. Equation of state, the ideal gas equation, we write here PV is equal to nRT, where PV and capital T are the pressure, the volumes and temperature of the gas, and N be the number of moles of the gas, and capital R be the gas constant. This equation is called this mathematical equation or this mathematical relation is called as a equation of a state. Then we consider next point, PV diagram. The graphical representation of a equation of a state of a system or gas is called the PV diagram or PV curve or a pressure volume curve or the indicator diagram of a system. The graphical representation of a equation of a state of a system is called PV diagram or a PV curve. It is also called pressure volume curve or the indicator diagram of a system. See here an indicator diagram for a ideal gas constant temperature. We draw diagram pressure versus volume. We consider here P1 and P2 be the initial and final pressure. Here we consider V1 V2, it is also initial and final volume. See these 2 points, A points which having coordinates P1 P1s and B points having coordinates P2 P2. See this diagram it indicates indicator diagram for an ideal gas at a constant temperature. The indicator diagram or PV curve for an constant temperature is called as a isotherms. The indicator diagram or a PV curve for a constant temperature, it is called as a isotherms. Okay. Then question asked on this topic, what is PV diagram? Draw an indicator diagram for an ideal gas at a constant temperature. What does this curve is named as? Okay, this indicator diagram or a PV curve for a constant temperature is called as a isotherms. Then we next see here PV diagram and explain concept of a positive and negative words. A gas conform to a cylinder with a movable frictionless and massless pistons can be expanded with varying pressure. It can also expand at a constant pressure. Figure shows the expansion of a gas at constant temperature. Its volume increases due to outward displacement of the pistons and the pressure of the gas decreases. Then the work done by the gas in this case is given by here W is equal to integration changes Vi to Vf to dW is equal to integration changes Vi to Vf P into dV. As dV greater than 0, the work done is positive here. See this diagram. Work means this area we consider P versus pressure versus volume. Here we see this PV diagram. Similarly, here we get integration change. This work done becomes integration changes V1 to V2 into PV into dV greater than 0. Hence, this work done is a positive. Second one, next one. Similarly, from second figure shows that compression this figure shows that compression due to inward displacement of the pistons, the pressure of the gas is increased and the work done by the gas is now negative as volume is decreases. See this diagram. Mm, here the pressure of the gas increase and the work done by the gas negative as volume is decreases. Okay. Question asked on this topic: draw a PV diagram and explain concept of positive and negative work. Gives one example of each. Then we discuss thermodynamic process. Firstly, we discuss what is by quasi-state processes. Quasi-state static processes means what definition is here. Processes in which change in the state variable of a system occur infinitesimally slowly are called quasi-static process. The process in which change in the state variable of a system occur infinitely slowly are called quasi-static process. During um, quasi-static process, the system is always thermodynamic equilibrium, always in thermodynamic equilibrium. Then we discuss path on a PV diagram. When a thermodynamic system changes from its initial state to its final state, it passes through a series of a intermediate state. This is a series of intermediate state when plotted on a PV diagram is called as a path. Path on a PV diagram. Uh, what is a path on a PV diagram? When a thermodynamic system changes from its initial state to its final state, it pass, uh, passes through a series of a indicator state. This is a series of a intermediate state when plotted on PV diagram is called as a path. Intermediate state. This is a series of a intermediate state when plotted on PV diagram is called a path. Note here, the path tell us where a system has gone through a change. Okay. Next one, PV diagram indicating change of state of a system from initial state V suffix I, comma P suffix I to the final state along the different possible path. See here, different way change of a system. This diagram shows a PV diagram indicating change of a state of system from initial state V suffix I, comma P suffix I to the final state along the different possible or state. Suppose this final state V suffix F, comma P suffix F. Next one, we consider the work done for a process in which the system changes state from initial to final along a path on which both pressure and volume changes. Another points, the work done for a process in which the system changes its state from initial to final along a path on which both pressure and volume changes. Consider a system changes its state from initial state. Suppose this initial state, consider here A, having coordinates v suffix I comma p suffix I, to the final state B with coordinates v suffix f comma p suffix f, as shown these figures. See these figures. A points consider coordinates v suffix I comma p suffix I, and B points consider coordinates v suffix f comma p suffix f. Okay, when the system changes itself from A to B, both its pressure and volume changes. The pressure decreases while volume increases. The volume done by the here work done by the system is given by the area under the curve. It is positive when the volume increases, as shown in this figure, or negative when the volume is decreases. Okay, in this way we discuss what work done by the system. Work done by the system is given by the area under the curves. Okay, volume this work done always positive when the volume increases, or work done is negative when the volume decreases. Here question asked on this topic: what will be work done for a process in which system change its state from initial to final along the path on which both pressure and volume changes? Then another one, last point, state here the state of system can be changed from initial to final in a different way. Firstly, we consider the system changes its state from A to B, as shown the following figures. Second condition, in this case the volume increases to V suffix I from the point A up to the point C at the constant pressure P suffix I. After point C, the pressure of the system decreases to P suffix I at a constant volume, as shown in following figure. And last one, the system thus reaches its final state B with coordinate V suffix f comma P suffix f. Work done in this process is represented by shaded area under the curve following. See this diagram. We consider four condition. Consider the system changes its consider consider the system changes its state A to B. Here A points A, and if we consider here B, shown this figure. In this case the volume increases to V suffix I from the point A up to point C here. Up to point C at a constant pressure P suffix I. After point C, the pressure of the system decreases to P suffix F. P suffix F at constant volume, as shown this figure. And last one, the system thus reaches the final state B with coordinate V suffix F, V suffix F, and P suffix F. Work done in this process is represented by shaded area. This is a work done. Work done in this process is represented by shaded area under the curve in this figure. In this way, we consider the state of system can be changed from initial state to final in a different way. Question asked on this topic: with the help of PV diagram, explain the work done by the system while expanding wine. First we consider here system undergoes first volume change at constant pressure and then the pressure change at a constant volume. Second question, system undergoes first pressure change at constant volume and the volume change at a constant pressure. And third one, in which case will the work done be more. In this way we complete this point. Firstly we discuss here what is by thermodynamic state variable. We consider two type of state variable. First one consider here intensive and another one is a extensive variables. Then we consider thermodynamic equilibrium. What is by thermodynamic equilibrium? We consider three condition: mechanical equilibrium, thermal equilibrium and chemical equilibrium. Then we discuss equation of state and also we discuss what is by PV diagram. And so once so in this way we complete this topic. Stop here. Thank you.